welcome back to AGT STEM. Today we're going to be watching a video about Promethium. So, without further ado, let's hop to it.
Many people don't think Promethium is very important, including the makers of my tie. You can see here praseodymium, neodymium, and Promethium is round the back. Promethium is element 61 between neodymium element 60 and samarium element 62. Now people realized that there must be an element between those two before Promethium was discovered. And the way that they argued this, the way that they thought that there must be an element, was by looking at atomic weights, relative atomic masses. So this is a book from 1922, which I bought as a second-hand book when I was a schoolboy. It has a table of atomic numbers and atomic weights. And down here, you can see the table of the atomic weights. Now it's called relative atomic mass. Between most of these elements, the difference in weight is somewhere between 2 and 3 units. Occasionally it's a bit more, but most of the time it's 2 or 3. And when you come to neodymium and samarium, the difference is 6. So the gap just seemed too big. So people thought there must be an element there. They went through many claims. We have found element 61, which turned out to be wrong. And the reason why none of them found it was because element 61, promethium, is radioactive. Its longest lived isotope has a lifetime of 3.7 years. The most common one is even shorter.
You mentioned that they deduced there must be one between neodymium and samarium because of the gap in the weights, in the masses. Couldn't they have done the same by looking at the valence of neodymium and samarium, what those things reacted with, and figured out, hang on, this one must have 60 electrons and this one must have 62, therefore there must be one with 61?
I think that when people started doing this, they didn't really know about electrons. As far as I know, Mendeleev didn't believe in electrons. And the other thing is that these elements, not so much promethium, but the other ones, can have variable valence, so they can make different numbers of chlorides or oxides. But it is true that one chemist deduced by looking at the reaction of hydrogen that neodymium reacted with 2 atoms of hydrogen, samarium reacted with none, so that he thought there should be an element that would react with 1 atom of hydrogen. So you see, Brady, you're really clever. It was only when the Manhattan Project, the nuclear weapons project, started in the United States, when there was a large amount of radioactive research being done, that enough radioactive isotopes were formed that people had a chance of detecting it. And in fact, the paper announcing the discovery of promethium, not by its name, but as element 61, was published just a few weeks, probably only 4 weeks before I was born. So I feel a certain resonance with this element. We were born at more or less the same time.
Still a very long time ago.
And so I've got the paper here, and what's interesting about this paper is that it is extremely modest compared to modern papers describing discovery of a new element, where there are press conferences, big ceremonies. You can see our video about some of these ceremonies. Here, at the end of a paragraph, it just says, in this paper is reported the successful separation of these 3 elements, the first to have been achieved with radioisotopes of neodymium, and these are the 4 words that describe the new discovery, and of element 61. You can't get much lower key than that. The paper is by 3 authors, Marinsky, Glendening, and Coriel, who were working at the Clinton laboratories at Oak Ridge, Tennessee. This is a laboratory that has been involved with the birth of many elements, Most recently, they participated in the synthesis of element 117, tennessine, which is named after Tennessee. Now, the way that these three authors separated promethium was by what was then a very new technique called ion exchange chromatography, in which they had a column of essentially plastic beads that had acid groups on it, and the element forms positive ions which can interact with the acid to form a salt. And if you have liquid flowing through the column, in this case it was a solution of a salt, then if you put in a mixture of metal ions at the top, the different elements are attracted with different strengths to the beads of this solid acid, and they come out at different times at the bottom. It turns out that the heaviest element comes out first, and they have...
That's pretty interesting. I guess that's an interesting way to like sort or figure out different elements. It's creative. It's creative.
Graphs which show how these different elements come out. Here, this is the key graph where they show the number of liters going along here and the amount of radioactivity that they measure. And there are different peaks, and this is the peak for element 61. Once they have isolated some solution with this element in it, they can distinguish it, say, from neodymium, because the radioactive decay has a different half-life, the energy of the electrons coming out is different, and so on. So they knew they had something different. I really like reading this paper. I read this one on the tram when I was going home. I got really excited by the time the tram got to the final stop. This element has had a number of different names when people have thought they've discovered it and hadn't, because in the old days there wasn't a committee that looked at the evidence before an element was named. So it was called, or people thought they would call it, illinium, presumably after Illinois, Florentium after Florence in Italy, cyclonium, I don't know what about, and finally Promethium. Promethium comes from the Greek legendary figure Prometheus, who stole fire from the gods. The naming was a reference to the discovery of nuclear weapons and, in a way, sort of stealing the power from the gods. The promethium is formed as a product from the nuclear fission of other elements. And I think it's important to realize that when, say, a uranium atom splits, not all the uranium atoms split the same way. So there are a number of different pathways, and one of them, a fairly minor pathway, leads to promethium. So once people started carrying out nuclear activities on a large scale, nuclear reactors, then in the reaction products, the fission products, they accumulated significant quantities of promethium so that you could start thinking about their uses. And there is one use which I think is fascinating of promethium, which is fairly short-lived. It was a good technology, but it didn't last very long, was making batteries, so-called nuclear batteries. There are a number of applications where you want a battery to last as long as possible. For example, heart pacemakers, when you have an electrical unit embedded inside somebody's chest. Thankfully, I don't have one. And you want the battery, in that case, to last as long as possible. Conventional batteries, even the ones in our phones, really don't last very long. As you probably know, you charge it up every day. But the idea was to make so-called nuclear batteries. And the idea of the promethium battery was that promethium decays by beta decay, that is, emitting an electron, which in itself is promising for making a battery because the electrons don't go very far, so it's easy to stop the electrons coming out of the battery. So the idea is that you mix the promethium with a material which, if the atoms are hit by an electron, they give out light, so-called phosphor. Phosphors used to be used on old-fashioned television screens where you had a coating which was bombarded by electrons and light came out so you could see the picture. So the idea is that you have a mixture of promethium and the phosphor which glows, light comes out, and you sandwich this between two photocells, and the photocells take the light and produce a voltage. And it has one enormous advantage over conventional batteries. A conventional battery like this one, or the ones you have in your cars, are very temperature dependent. If the weather's very cold, it's difficult to start your car because the battery has lower voltage. The Promethium battery was much less temperature dependent. So it could be cooled to very low temperatures and potentially, say on a spacecraft, and would still produce a very similar voltage because it was not relying on a chemical reaction but on this photoelectric effect. The problem, and the reason why the technology has now largely been superseded, is that the half-life of the promethium is very short. So the amount of promethium in your battery decayed by half every 2-point-something years. So if you were trying to travel to a distant star, the battery would have gone flat long before you got there. If you want one...
Thank you so much for watching. Hope you found that video interesting. Promethium is pretty interesting. I had so many different names for it before they finally agreed on one. Thank you so much for watching, and we'll see you next time. Stay smart. Bye!